Let us now proceed to section 1.2, which is on solutions of differential equations. Whenever we are able to solve a problem, we get an answer, and the answer is known as the solution to the given problem. And so, a solution of a problem in differential equation is defined as any function that satisfies the equation on an interval I. The function y of x is said to be a solution of a differential equation of nth order if y and its derivatives satisfy the equation for every value of x on the interval I. The interval I refers to the domain of the independent variable. The interval can also be called as the domain of the solution, or the interval of definition, or the interval of existence, and a solution must be continuous over the interval I. Okay, I will explain some of these terms in this slide by showing you some examples of problems. This chapter 1, does not teach us the techniques of solving a differential equation. Instead, it gives us a function that is said to be a solution of the differential equation. So in this section, we are interested to verify or prove whether a function is a solution of a differential equation. So how do we go about verifying or proving that the given function is a solution of the differential equation? Let us look back at the definition of solution as given in the previous slide. A solution of a differential equation is defined as any function that satisfies the equation on an interval I. So in other words, if we want to verify that that function is a solution, what we have to do is to simply substitute the function and its derivatives into the differential equation and then check whether the result is the same on each side of the equation. In other words, if we have been able to show that the left-hand side of the equation is the same as the right-hand side of the equation, after substituting the function and its derivatives into the differential equation, so that shows that the function has satisfied the equation and therefore it is a solution of the differential equation on the given interval I. For example, verify that the function y equals to 2 sine 3x plus cos 3x is a solution of the differential equation y double prime plus 9y equals to 0 on the interval minus infinity to infinity. So in this problem, we are given the function, and this function is said to be a solution of this dE. So how do we verify, or how do we prove that this function is a solution of this dE? What we need to do is to substitute y into this part of the differential equation and then differentiate y twice and substitute y double prime into this part of the differential equation, and we get the sum of these two terms and see whether the left hand side is equals to the right hand side, which is 0, and if both sides are of the same value, then we conclude that the function has satisfied the differential equation and therefore this function is a solution of the given differential equation on the interval minus infinity to infinity. Now this interval minus infinity to infinity means x can be any real number. This interval refers to the domain of the independent variable x. So this function, which is the solution, must be a continuous throughout this given interval. Let us now learn the steps of verifying that the given function is a solution of the given dE. Okay, now this is the function y equals to 2 sine 3x plus cos 3x, and we need to substitute y into this part of the dE, and we also need to substitute y double prime. To find double prime, of course, we need to find y prime first. So if y equals to 2 sine 3x plus cos 3x, then y prime will be, we're going to differentiate the first term, 2 sine 3x, we get 6 cos 3x, and differentiate the second term cos 3x with respect to x, we'll get negative 3 sine 3x. So this is y prime. Now y double prime is equals to differentiate the first term of y prime, differentiate 6 cos 3x with respect to x, we'll get negative 18 sine 3x, and differentiate the second term of y prime, differentiate negative 3 sine 3x with respect to x, we'll get negative 9 cos 3x. So we proceed by substituting y and y double prime into the left-hand side of the given differential equation. So the left-hand side is given by y double prime plus 9y, and substitute y double prime, which is negative 18 sine 3x minus 9 cos 3x, plus 9 times y. 9 times y, now y comprises of two terms, therefore these two terms must be placed inside a bracket, because 9 need to be multiplied by each of the term in y. Open up the bracket, we'll get negative 18 sin 3x minus 9 cos 3x plus, now 9 times 2 is 18, 18 sin 3x plus 9 cos 3x. So 9 cos 3x cancel with negative 9 cos 3x, 18 sin 3x cancel with negative 18 sin 3x. Okay, so after simplifying, we get the result as equals to 0, which is exactly the same as the right hand side. So we have managed to show that the left hand side is equals to the right hand side. So what is our conclusion? Okay, our conclusion is that since this function has satisfied the differential equation, and therefore it is verified that the function y equals to 2 sin 3x plus cos 3x is a solution of the differential equation y double prime plus non y equal to 0 on the interval minus infinity to infinity. A solution which is exactly equals to 0 on an interval is known as the trivial solution of the differential equation. In other words, if we solve the differential equation and the result is a function y equals to 0, that y equals to 0 is known as the trivial solution or an easy solution of the differential equation. In the previous example, we looked at this differential equation y double prime plus 9y equals to 0, and we have verified that the function y equals to 2 sin 3x plus cos 3x is a solution of this differential equation. Now what about the function y equals to 0? Let us substitute y equals to 0 into this part of the equation, and we differentiate y equals to 0 twice, which is also 0. So 0 plus 9 times 0 is also equal to 0. So it seems that the left hand side is equal to the right hand side. And so we say that y equals to 0 is a solution of this given differential equation. But to be more specific, we call y equals to 0 as the trivial solution. So y equals to 0 is the trivial solution for this differential equation y double prime plus non-y equals to 0. When we solve a differential equation, we get the solution, and that solution can be sketched in the form of graphs. So the graph of a solution is called a solution curve. So some solution curves can be sketched manually, but most of them can be obtained by using certain softwares. Forms of solutions. The first form of solution that we are going to discuss is an explicit solution. An explicit solution is a type of solution in which the unknown y appearing in the solution is a linear function, and it is expressed solely in terms of the independent variable x and or constants. In other words, an explicit solution has the explicit formula y equals to f of x, where f of x is a function of x alone, including constant functions. So if you are given a differential equation and we solve the differential equation, the solution of the differential equation is a function, and if that function is expressed explicitly in the form y equals to f of x, then that solution is known as an explicit solution, where y is a linear function. Okay, y is a linear function, y is to the power of 1, and the function f is expressed solely in terms of x, including constant functions. In the previous example, we have seen that the function y equals to 2 sine 3x plus cos 3x is a solution of the differential equation y double prime plus 9y equals to 0 on negative infinity to infinity. This function is expressed in the form of y equals to f of x. Okay, so y is a linear function, y is to the power 1, and it is expressed solely in terms of the independent variable x. So when the function is expressed explicitly in the form of y equals to f of x, then this function can also be referred to as an explicit solution of the differential equation y double prime plus 9y equals to 0. Similarly, for the trivial solution, y equals to 0, y is a linear function and is expressed explicitly in terms of a function in x which includes a constant, is also an explicit solution of the differential equation y double prime plus 9y equals to 0. So in order for us to verify whether a function is an explicit solution of a differential equation, the technique is the same as what we have discussed before, that is, simply substitute the function and its derivatives into the differential equation and check whether the result is the same on each side of the equation. The second form of solution is known as an implicit solution. An implicit solution is any solution that is not in explicit form. Okay, so a solution is said to be implicit if it involves a relation f of xy equals to 0 that expresses y implicitly as a function of x. In other words, that function cannot be expressed in the form of y equals to f of x. Okay, the function y cannot be expressed explicitly in terms of x. Y is expressed implicitly as a function of x, hence the function is said to be an implicit solution of the given differential equation. So how do we verify that a given relation is an implicit solution of a differential equation? The technique is by applying implicit differentiation. Okay, so let us look at example 1.6. The question is, the relation x squared minus 3y plus y squared equals to 0 is said to be an implicit solution for the differential equation dy dx equals to 2x over 3 minus 2y on minus infinity to infinity. Verify. Because we have to prove or we have to verify that this relation is an implicit solution of this dE. Okay, that means if we solve this equation, we will get this result. And notice that this expression cannot be written in the form of y equals to f of x. Y cannot be expressed explicitly in terms of x, and therefore this relation is said to be an implicit solution. Okay, so now let us now verify that this relation is an implicit solution. Let us proceed by verifying that this relation x squared minus 3y plus y squared equals to 0 is an implicit solution of the given differential equation. To start with, we are going to apply implicit differentiation to the given relation. That is, we write d dx of x squared minus d dx of 3y plus d dx of y squared equals d dx of 0. Okay, so we differentiate each term on the left side of the equation with respect to x, and we also differentiate the right side with respect to x. When we differentiate x squared with respect to x, the answer is 2x. Differentiate negative 3y with respect to x. Using implicit differentiation, the answer is negative 3 dy dx. Plus, differentiate y squared with respect to x. The answer is 2y dy dx. And differentiate 0 with respect to x. The answer is 0. The next step is to simplify and rearrange this expression and check whether we will finally get an expression identical to the given differential equation. Notice that these two terms have common derivative dy dx, so let us factor dy dx to get the following form: 2x plus 2y minus 3 dy dx equals to 0. We can now shift 2x to the right side, so 2y minus 3 dy dx equals to negative 2x, and then divide the whole equation by this factor 2y minus 3, so dy dx equals to negative 2x divided by 2y minus 3. Multiply the numerator by negative 1 and multiply the denominator also by negative 1. So we get the form dy dx equals to 2x divided by 3 minus 2y. And notice that this expression is exactly the same as the given differential equation. So let us make our conclusion. We say that the above form, which is this one here, is identical or exactly the same, identical to the form of the given differential equation, and therefore the given relation is an implicit solution of the differential equation on the interval minus infinity to infinity. Okay, so this is an example of how we apply implicit differentiation to verify that a given relation is an implicit solution of a given differential equation. Okay, here are some more important terminologies that we should know. The first one is on the term general solution. A general solution is a solution that involves one or more arbitrary parameters. For example, suppose we are given a differential equation y prime equals to 4x, and the solution of this differential equation is y equals to 2x squared plus c. Now this solution consists of an arbitrary parameter c. Now c can be of any value. C can be 0, c can be half, c can be negative 10, and so on. So, since c can be any number, we say y equals to 2x squared plus c is the general solution for the differential equation y prime equals to 4x. A particular solution is a solution of a differential equation that is obtained by assigning particular values to the arbitrary parameters in the general solution. Okay, just now we said that c can be of any number, but if we have assigned c to be a specific number, for example, we assign c to be the number negative 2, then this function y equals 2x squared minus 2 now is known as the particular solution for the differential equation y prime equals to 4x. So if we replace c by another number, let's say we replace c by the number 10, then we say y equals to 2x squared plus 10 is the particular solution for the differential equation y prime equals to 4x. Families of solutions. An nth order differential equation possesses an n-parameter family of solutions. In the previous example, we have seen that y equals to 2x squared plus c is known as the general solution for the differential equation y prime equals to 4x. Now, this function consists of one parameter, so we can also call this solution as a one-parameter family of solutions of this differential equation. Another example is that this is a second-order differential equation, and the solution for this differential equation y double prime plus y equals to 0 is y equals to c1 cos x plus c2 sin x. This solution consists of two parameters, which we label them as c1 and c2. Since there are two parameters existing in the solution, so we call this function as a two-parameter family of solutions of the differential equation y double prime plus y equals to 0.